Hello, uh, welcome to the chapter Statistical Mechanics. And in this class, I'm going to derive an expression for the Fermi Dirac distribution. And first, we will see what are the characteristics of this Fermi Dirac distribution. So, the first point is that the particles are identical but indistinguishable. So the particles are identical, but they are indistinguishable. This is the first point. And a state can be occupied by not more than two particles. So this is very important. This is the quantum rule because it is actually the Pauli's exclusion principle. So this Pauli's exclusion principle is obeyed by the Fermi-Dirac distribution, and the Pauli's exclusion principle tells that no more than two electrons can occupy the same state. So that is a restriction. So that restriction is obeyed by this distribution, Fermi-Dirac distribution, and because of this reason, it is called as the quantum distribution. These are the particles with half integral spin, and examples are electrons, positrons, etc. And internal energy at absolute zero is not taken as a zero because the quantum rule tells that, or the quantum mechanics tells that, even though the system is at absolute zero, it will have certain minimum energy that is called as a 0 point energy. So that is the reason why we are not taking the internal energy at absolute zero as a zero, and it obeys the quantum laws. The most probable distribution The most probable distribution is given by Ni is equal to Gi divided by e raised to alpha plus beta Ei plus 1, and we are going to derive this equation in this session, and these are called as the fermions. So all the particles which are obeying the Fermi-Dirac statistics are called as the fermions. So that is the general name or the common name. Next, I will see. We'll come to the derivation part. So the Fermi-Dirac distribution derivation we have to start in this way, and the derivation is just like the earlier two derivations which I have done for the Maxwell-Boltzmann and the Bose-Einstein distributions. So consider a system of n identical indistinguishable particles. Let n1, n2, dash 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 ni or the group of particles having constant energies E1, E2, dash 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 Ei respectively. Therefore, the total number of particles capital N is equal to N1 plus N2 plus dash 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 Ni, that is equal to constant. And the total energy of the particle is given by Et is equal to E1 N1 plus E2 N2 plus dash 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 Ei Ni is equal to constant. So here E1 is the constant energy possessed by every particle present in the group N1. So that is the meaning. And we can write the equations 1 and 2 in this form. So that is N is equal to summation over I, Ni, and Et is equal to summation over I, Ei, Ni. So equations 1 and 2 can be written in this way using the summation symbol. Then differentiating above equations will get dn is equal to summation over I dni. This becomes 0 because this ni is constant. So differentiation of any constant is 0. So this becomes 0. And this differentiation of this et is det is equal to summation over I ei dni is equal to 0. So because that quantity is also a constant, so its differentiation is a 0. So next, in this distribution, the particles are identical and indistinguishable. So our task is to distribute Ni particles into Gi cells. And as the particles are indistinguishable, some of the arrangements will have to be omitted because they are the repetitions. They are the repetitions of some earlier arrangements. So some arrangements will have to be omitted, which are repeating. So therefore, Ni particles can be arranged in Gi cells in the following way. So that is a Gi factorial divided by Ni factorial into Gi minus Ni factorial. So in this way, the particles can be arranged in Gi cells. So therefore, the probability of occupancy of Gi cells by Ni particles is thus given by P is equal to product over I, Gi factorial divided by Ni factorial into Gi minus Ni factorial. Then taking the log on both sides of this equation 5, we get log P. Log P is equal to log of this RHS of the equation 5 is there. And next, so this log operates on this product over I symbol, so it becomes summation, and log of Gi factorial divided by Ni factorial into Gi minus Ni factorial is there. Next, apply the logarithmic rules. So this becomes log of Gi factorial minus log of Ni factorial minus log of Gi minus Ni factorial after applying the logarithmic rules. And in this stage or in this step only, I am going to apply the Stirling's approximation, that is log of n factorial is equal to n log n minus n. So that is applied here. So Stirling's approximation is applied to this term, log of Gi factorial term. So it becomes Gi log Gi minus Gi. And next I will apply the Stirling's approximation to this term. So this becomes minus Ni log Ni plus Ni, because already minus Ni is there, and this minus minus get plus. So it becomes plus Ni. Similarly, apply the Stirling's approximation to the last term. So it becomes Gi minus Ni into log of Gi minus Ni and plus Gi minus Ni. So in this way, we apply the Stirling's theorem. And you see here, this minus Gi plus Ni and this get cancelled, and you write the remaining things. It becomes Gi log Gi minus Ni log Ni minus Gi minus Ni into log of Gi minus Ni. So we left with these terms. Next, we have to differentiate this equation. So therefore, differentiating. So d log of omega is equal to summation over I, and the differentiation of this first term is 0, because it's all Gi is there. Gi is a constant, so therefore it becomes 0. The differentiation of this term becomes 0, and it will differentiate this term using the product rule. So it is Ni into 1 by Ni di minus log of Ni into dni. So differentiation of this term is over. Next, differentiate this term again using the product rule. So you have kept this term as it is, and the log of Gi minus Ni is differentiated here. It is 1 by Gi minus Ni into minus dni. Actually, it is dgi plus dgi minus dni. As dgi is 0, we will get this term. It is minus dni only left here. Next, plus dni. Dni means the log of Gi minus Ni is kept as it is, and we are differentiating Gi minus Ni. So differentiation of this gives plus dni, because differentiation of the Gi is 0, and only the differentiation of Ni becomes dni, and minus into minus is plus. So in this way, we differentiated the above equation. Again, so many things get cancelled here. Ni get cancelled, and this factor and this factor, this term get cancelled, and this becomes plus dni. This becomes minus dni. So they also get cancelled. So lastly, we left with these two terms, and apply the logarithmic rule, and summation of dni is common in both the equations. So it becomes a summation over I dni into log of gi minus ni divided by ni after applying the logarithmic rules. So next, in the steady state, omega is constant. So there and thus d log of omega becomes zero. That means the LHS of equation 6 becomes 0, and therefore the equation 6 becomes summation over I dni log of gi minus ni divided by ni is equal to 0. So this is the equation 7. And multiplying equation 3 by alpha and equation 4 by beta. Equation 3 is a summation over I dni, so that is multiplied by alpha, and equation 4 is summation over I ei dni, that is multiplied by beta, and subtracted from equation 7, we get in this way. So it is summation over I dni log of gi minus ni divided by ni factorial, and these terms we are subtracting. That means equation 3 is multiplied with alpha and subtracted, so this is the term, and equation 4 is multiplied by beta and it is subtracted, and this is the term. Next, summation of dni is common in all the terms, so it is taken out and sent to the RHS. It goes to 0. So we are left with this thing, and you take this minus alpha minus beta to RHS side. The above equation becomes log of gni minus ni divided by ni is equal to alpha plus beta ei, and you remove the log on LHS side. The RHS goes exponential, so therefore it is gi minus ni divided by ni is equal to e to e raised to alpha plus beta ei. And this term we have to simplify, take a separate the LCM. It is gi by ni minus ni by ni. Ni by ni is get cancelled, so it is 1 is equal to e raised to alpha plus beta ei, or this is equal to gi by ni is equal to this minus 1 term is there, it is taken onto the RHS, so it becomes plus. So it is e raised to alpha plus beta ei plus 1. And lastly, we arrange the rearrange the terms. We will get this as ni is equal to gi divided by e raised to alpha plus beta ei plus 1. So this is the final expression for the distribution of the Fermi Dirac distribution. So on this, it is very easy to derive, and very useful for and very important for the examination point of view. Out of these three derivations, one will be asked definitely, and prepare accordingly. Thanks for listening.